we are going to consider how to find the equation of a slant or oblique asymptote. If function given is one polynomial function divided by another polynomial function like this, slant asymptote exists only if the greatest power in numerator is one more than the greatest power in denominator. And actually slant asymptote, it's about limit when x tends to plus or minus infinity, and hence we analyze only the greatest powers of x, terms containing the greatest powers of x, and discard other powers because they will be much less when x tends to plus minus infinity. So how to find required equation of slant asymptote? The first way is just using a formula, and actually since slant asymptote as any other straight line has equation mx plus c, and we need to find m and c. M can be found using the next formula. It's limit x tends to infinity function divided by x. So for this example, it becomes x limit of x squared plus 1 over x squared minus x. And how to find limit? Again, since x tends to infinity, we analyze only terms containing the largest power of x in numerator and denominator and ignore other terms, and we can see the same power, hence limit just coefficients in front, so it's 1 over 1, x squared can be just cancelled out, so limit is just 1 over 1 or just 1, so m is 1. C can be found using the next formula. It's also limit function minus mx, and for our problem it becomes function minus 1x, or just minus x, and it is equal to limit x tends to infinity x squared plus 1x minus 1 minus x. We do common denominator, and it is equal to x squared plus 1 minus x squared plus x. It is equal to limit x plus 1 x minus 1. Again, the greatest powers are the same, so limit exists and is equal to just 1 over 1 is 1, hence c is 1. So required equation of a slant or oblique asymptote is 1x plus 1 or just x plus 1. Another way to find slant asymptote is I try to make in numerator multiple of denominator. So I need in numerator multiple of x minus 1. I can see x squared. So if I subtract x and add x, I don't change numerator, but because it's just 0. But now if I split it into two fractions, it becomes x squared minus x over x minus 1 plus x plus 1 over x minus 1, and here if we factor out x, we get x minus 1 x minus 1 can be cancelled out, and I get x plus 1 over x minus 1. And actually slant asymptote is about limit when x tends to plus minus infinity, and here we can see same power in numerator and denominator, so limit is 1, so I can write that it's x plus 1, or to be more clear, I can do the same here. So I want to make multiple of x minus 1 in numerator, so I can subtract 1, add 1, plus 1 x minus 1, and split it into two fractions to get x minus 1 over x minus 1 plus 2 over x minus 1, which is equal to x plus 1 plus 2 x minus 1. And now it's clear then when x tends to infinity, this tends to 0, and it's directly equation of a slant asymptote. The next way is just to divide polynomial, but I can do that using synthetic division or long division, and it's actually, according to remainder theorem, I can represent any polynomial as x minus a in general multiplied by another polynomial plus remainder. And since there is x minus 1, so I want to represent x plus 1 as x minus 1 sum of the polynomial plus remainder. And by definition, remainder is a polynomial at point A, and if a is a root, hence remainder is 0. So to find q and remainder, I just divide x squared plus 1 by x minus 1, and using synthetic division I write 1 here. If we divide by if we divide by x minus 1 or x minus a, here should be a. So x minus 1 here must be 1. And here we write coefficients of polynomial of degree of 2, so there must be 3 coefficients. Coefficient in front of x squared 1, coefficient in front of x 0, coefficient just number, it's 1. And here we write this, just copy, and then this multiplied by this, and right answer here 1 times 1 is 1. Then add these numbers. X 0 plus 1 is 1. Again 1 times 1 right here. 1 times 1 is 1 right here. And again add these numbers to get 2. And the last number is remainder always. And these numbers give q, and q is a polynomial 1 degree less than initial, so it's polynomial of degree of 1, and these coefficients with these coefficients, so it's 1x plus 1. So x squared plus 1 is x minus 1 multiplied by x plus 1 plus 2, or if we divide by x minus 1, we get x squared plus 1 over x minus 1 is x plus 1 plus 2 over x minus 1. And again, it just equivalent, and now it's clear that when x tends to infinity, this tends to 0, and it's required equation of a slant asymptote. I can get absolutely the same result, but using long division, so I just divide x squared plus 1 over x minus 1, and I need such a value so that if I multiply by the greatest power here, I should get the greatest power here. So it must be x, and now I multiply x by x minus 1 and get x squared minus x. The next step is this row minus this row, so it is equal to 1 minus x. I write x firstly, x plus 1, and the next I should choose such value so that when it is multiplied by x, I should get x, so it's 1, so it is 1 multiplied by x minus 1 is x minus 1, and again this row minus this row, so 1 minus 1 it's 2, and its remainder. Hence you can see that x squared plus 1 is x minus 1 multiplied by x plus 1 plus 2. So it's absolutely the same, but another way to divide. Another example. The asymptotes of the graph y is intersect at the point where bk are real. Find the value of k and the value of b. So we can see that when x minus 3 is 0, we get vertical asymptote, so x is 3 is vertical asymptote. It means when x tends to 3, y tends to plus or minus infinity. It looks like this. X is 3, and we can see that the greatest power in numerator is 1 more than in denominator, so we have slant asymptote here. I don't know actually gradient or y-intercept, but it doesn't matter. And vertical and slant asymptotes intersect at point k5, and we can see that k is 3, k is found, and to find b we need equation over a slant asymptote, and since now we know that 3, 5 point which belongs to equation of a straight line, which is equation of a slant asymptote, and then if we substitute 3, 5 into equation of slant asymptote, we can get equation with respect to b. So we need equation of a slant asymptote. Let's find it. The first way is to use formula. Let's use formula, and m is limit x tends to infinity function over x, so it is equal to limit x squared plus bx plus 4 over x squared minus 3x. Again, when x tends to infinity, we analyze only the greatest powers of x, other can be ignored, and since we have same powers, limit it's just 1 over 1, just coefficients, and which is 1. So m is 1. M is 1, and c is limit function minus mx, and it becomes minus just x. In general, f minus mx. For our situation, it becomes minus 1x, and it is equal to x squared plus bx plus 4 over x minus 3 minus x, and make common denominator. It becomes minus x squared plus 3x, which is equal to limit, and in numerator we can factor out x, and again we analyze only the largest powers of x, and we can see same powers, and limit is just b plus 3 over 1 or just b plus 3. Hence c is b plus 3. So equation over slant asymptote is x plus b plus 3, and we know that 3, 5 belongs to this line, so we can just substitute 5 for y, 3 for x, and find that b is -1. And now let's consider other ways how to find equation over slant asymptote. Another way is just I try to make in numerator multiple of denominator. So I can see x minus 3 and there is x squared, so I can subtract 3x and add 3x, so that I get x minus 3 plus b plus 3x plus 4 over x minus 3, and if I split into two fractions, it becomes x plus b plus 3 x plus 4 over x minus 3. And again, slant asymptote is about limit when x tends to infinity, and if we consider this expression, we can see we actually analyze the greatest powers of x, and we can see same powers. So limit is just b plus 3, or actually we can also split it into two fractions to be it more clear. It is equal to x plus x minus 3. So b plus 3x minus 3b plus 3 plus 3b plus 3 plus 4. It's 0. I just subtract and add the same expression, and now you can see that hence we get, if we factor out b plus 3, we get x minus 3 and plus 3b plus 3 plus 4. And now if we split it into two fractions, we get x plus b plus 3 plus 3b plus 3 plus 4 over x minus 3. And now it's clear that when x tends to infinity, this tends to 0, and it's required equation over a slant asymptote. And another way is just to divide polynomial functions, and I can do that using synthetic division or long division. So for both, I try to represent x squared plus bx plus 4 as x minus 3 multiplied by another polynomial plus remainder, or if we divide, we get x squared plus bx plus 4 over x minus 3 is q plus remainder over x minus 3. So if we make x minus 3, I write 3 here, and coefficients are 1, b, and 4. Just copy 1 here and then 1 multiplied by 3 and right answer here. It's 3. B plus 3, add these values. Again, this multiplied by this and right answer here. So it's 3b plus 9 and add these values. Becomes 3b plus 13, and it's the last value. It's always remainder, and these coefficients give polynomial 1 degree less, so it's x plus b 1x plus b plus 3, it's q. Hence, x squared plus bx plus 4 over x minus 3 is x plus b plus 3 plus 3b plus 13 over x minus 3. And again, when x tends to infinity, this tends to 0, and it's required equation of a slant asymptote. I can get the same using long division, so I just divide x squared plus bx plus 4 over x minus 3. So I choose such value so that if it is multiplied by x, I should get the greatest power here. So it's x multiplied by x minus 3, it's x squared minus 3x, and this row minus this row. It is equal to b plus 3x plus 4. And again, I need such value so that if I multiply by the greatest power here, I should get a term which is equal to the greatest power here. So it's plus b plus 3. So b plus 3 multiplied by x minus 3 becomes b plus 3x minus 3b plus 3. And again, this row minus this row, which is equal to 4 plus 3b plus 3. And again, it's remainder and it's result of division. So we get absolutely the same, but another way to divide. And that's all.